Welcome everybody to week 13, day 2. Networking is a topic that I have taught in various classes at various times over various years, and I've never been happy with any of them. The C++ standard doesn't, well, it technically has networking as part of it, but the networking that it has is from the C world days, and so they are rather gnarly looking. If you want to see what it looks like, cd server vim main.c because it's nope vim server.c. This is C, not C++, and this is what your thing's going to look like. These are actually wrapper functions that I wrote to make it look nicer than it already is. And even still, you can see there's all these random structs, and it listens on a string file descriptor, and it sits there and waits until somebody connects, and then it fills in the data into the data struct, and then you call these functions, inet, network to address, and you have an array of file descriptors, and I have functions to write to the different network ports and wrapper functions to make it look nice, and it's actually pretty gnarly. So I've got this whole wrapsock library that was adapted from somebody, and like the code just looks like somebody took spaghetti and slapped it against the monitor. Things like that, and these are actually nice functions that just make it nicer than this is the low level stuff. So in C++, if you want to do networking, you've got functions like bind and connect and accept and things like that, and it's listen, of course, and they work directly on file descriptors, which are integers. So you think a file is like a file. Nope, it's just an int. In Unix, at the lowest level, a file is just an integer. What file is that? 27. All right, cool. So when you open a file on Unix, it gives you an integer. Now you don't see that because you're used to working with like iostreams and stuff like that. No, man to open. So when you open a file in Unix, you give it a path name to a file. You give it the flags, the permissions you want it to open with and stuff, and it gives you an integer. Congratulations, you've opened the file. It is file 30, and you have to hold on to that, somewhere. And that's why the C library has what's called a file pointer, and C++ is an iostream because it keeps track of the integer for you and does buffering and some other stuff. But why do we keep saying vim instead of man? Man to write. And when you want to write to a file, you pass it a file descriptor. Write to file number 30, and you pass it a memory address and how many bytes to write. And that's how you write files. It's also how you write to the network. So at the lowest level, when you have a connection, a network connection, it's just a file descriptor also. And so you can write data to the network just like you write data to disk. Or you can, if its file descriptor is 0, that's the keyboard, and file descriptor 1 is the standard out, and file descriptor 2 is the standard error. And so if you were to pass in 1 there, the data that you write will appear on the screen. If it's from a file you've opened, it goes to a file. If it's from a network socket, it goes to the network socket. Read, write, and open and close are your basic underlying functionality. And a lot of people over the years have... So what is a socket? Good question. So the metaphor used is kind of like the socket in your house, right? Like a power socket. And you don't know how power gets to your house, right? I mean, sort of vaguely, there's like some wires, and like somewhere out there's like Bass Lake has got a power generator on it or something, but it's sort of abstracted away. Like you don't really know whose electron that is coming out of the wall, right? All you know is that you plug your lamp into it and hit the power switch and the light turns on. And that's the metaphor used for, I thought it was just magic. Yeah, that's the metaphor used for networking. So with a socket, you type in somebody's IP address, like connect to Google, right? And the network figures it out. And when you connect to Google, and to in order to open a network socket, you do connect, and you pass in this sock adder pointer thing, which holds the information to connect to something over the internet. It's got like an IP address and port number and stuff like that. And you basically pass it google.com, port, whatever, 80. And then it connects or it doesn't. And basically once it's connected, connects the socket referred to the file descriptor, socket file descriptor to the address. Yeah, so that's you've created a file descriptor already, and then you connect it to Google. But after you've done this, you just push data into that socket. You just put electricity into that socket, and then Google pulls out of its socket. And if you put in 10, 20, 30 into your socket, Google reads out 10, 20, 30 out of its socket. It's magic. Okay, so you're right. It is magic. So it's like plugging into the network. Exactly. So the underlying details of how the internet works is abstracted away. You don't need to worry about how you route, because like here in my house, I've got my computer and it's connected to this Wi-Fi router up here by Ethernet, and then that's got a cable coming out through the wall and going through a conduit over to the local, where's Hazleton? He does this for a living. There's a box where it's a utility box where all the local AT&T has one and Comcast has one, and then that connects to that, and then that connects to that, and so on and so forth. None of that matters. All you do is you say connect to Google, and if it works, this socket, which is just an integer, 50, is connected to Google, and you can call write. You can call write and pass in 50. That's my connection to Google, and whatever data you have there, and it's a void pointer. It means no type. You just give it literally a memory address. A void pointer is just a memory address. So you pass in memory address and how many bytes in that memory address to write, and that data will fly magically across the network and end up in Palo Alto or wherever their data center is, and their server will read the exact same bytes out that you put in, and it's just magic. Okay. So C code makes you want to commit not living. Yeah. And it's so gnarly, like it's so annoying to work with that many people over the years have created abstractions to try to make the networking not suck, right? And so the code I'm going to show you is my latest attempt to teach it in such a way that it is network. It's a network demo. Then server.cc. Which one is this? Oh, this is using ZMQ. No. I tried doing that with like JT and Walker, and yet another failed attempt to make networking easy. But maybe this one is finally it. The Boost iostream interface, because it works just like iostreams. You guys all remember iostreams from C++, C in, C out, that kind of stuff. So basically, rather than C in and C out, you C out to the network, and you C in from the network. And if you can C in and C out to the screen and keyboard, you can connect to a server and read and write to it and stuff like that. So I've got this server running right now. The server looks like this. Then daytime server.cc. This is the whole program. Okay, so it's kind of gnarly looking. It's got a lot of colons because people love themselves some colons. And I don't think we actually even need these because they put a using into it. So I think we could probably just drop that. Drop that. Nope. Guess not. Okay, so IO context is their own, and I've used ASIO in the past and tried teaching students ASIO, and it explodes their brains. But basically, what this is doing, just ignore that. That's just its thing. Whatever. An endpoint is like a socket. Okay, kind of. So it's saying we're going to be listening. Do you guys know the difference between IPv4 and IPv6? Yeah, Bridges actually abstracts away the networking nicely. You actually barely even notice the fact that Bridges is over the network, except when your credentials don't work, right? So yeah, let's have a bit of history. So let's explain internet stuff. So IPv4 is the default way of transmitting over the internet. If you have ever seen a network address like this, have you ever seen this stuff? 172.16.254.1. Have you ever seen, like, sometimes people do, like most of the time, we do them like this, like wikipedia.org. But you might have seen, have you ever seen this before? Like a 4 octets. 127.0.0.1. Have you guys never seen that? Okay. So that's what an IP address looks like in IPv4. It's 4 bytes, basically. Each byte goes from 0 to 255. And each one of these will uniquely specify a host on the internet. Now you might be like, wait, that doesn't seem like very many hosts. It's 255 times 255 times 255 times 255. And you would be right. What is max int? 4.2 billion and change. How many people are there in the world? More than 4 billion. How many devices do I have? I don't know. A lot. You know, so even if you gave one IP address per person, it's not enough. Let alone the fact that I've got a cell phone and this computer and that computer and the laptop and all that other stuff. So, hey, Tristan's here. Yeah, it's all just zeros and ones. I'm just an artist that works with zeros and ones, my lord. Yeah, so IPv4 was created in a different world. It was created at sort of the dawn of the internet, back when you could actually know everybody on the internet. Okay? And so you could actually have a map of the internet. Here's every machine on the internet in 1977. Right? And so UCSD... Like, one of my professors was actually the guy. Here's UCLA. Here's USC. My professor at UCSD was actually one of the guys who tracked all the hosts on the internet. That was his job. And you go look at it. There's like, I don't know, like 100 or so, you know? And so if something went wrong, he would, like, call up MIT. It's like, yo, by the way, this PDP-11 here, it's, like, going crazy, man. You need to take care of that. And they're like, oh, I'm so sorry. And they would fix it, you know? And so he literally knew all the system administrators on the internet, and he would just be like, yo, hey, one of your guys, I don't want to be that guy, but one of your users mentioned that they were a lawyer, and they said, hey, if you need any law services on this mailing group, and he gave his phone number, and that's kind of like advertising, and we don't allow advertising on the internet, so... could you please, like, I don't want to ban him or anything, but, like, could you please talk to him and just be like, you know, like, he can have his, like, contact information on it, but don't, like, solicit, you know? And this is actually what happened. Like, a lawyer was like, hey, by the way, if you need advice on this, you know, give me a call. You know, and people are like, whoa. Not cool, dude. This is the internet. We don't allow advertising on it. And that would have been around 94 or so. It's a little different now, you know? And so Yeah, it was a different world, and you can see which machines are connected to which machines and things like that. And so, like, if you were here at UCLA and you wanted to send an email to MIT, what you do back in the days, you'd actually have to specify the routing. You would say, send a message to MIT, and you'd use a bang, an exclamation mark. You'd say, send it to USC, send it to DocB, whatever that is, send it to GWC. And you'd actually have to manually choose the routing, and then the mail clients would pull off their host name, USC, bang, you would pull it off and see, okay, it's to DocB, and it'd send it to DocB, and then DocB would pull it off in the bang. And so you actually had to manually route email addresses back in the day. And then a maximum size length of 256. And if you exceeded it, it would crash the server. It would crash the router. And so the upstream node would then try retransmitting it on a different router on the same thing and kill it again. And so, like, the world was a different place back then. Hawaii over a satellite circuit. You know, so anyhow, so they were not intending this to be something that people would have a Internet of Things, right? Where, like, your air conditioner has an IP address and your car has an IP address. Like, it was made for a different world. And so people very quickly realized that this was a problem. Back in the 90s, when the internet was exploding, they realized very quickly that 4.2 billion IP addresses was not enough. Especially the way they allocated it, like 1/256th of the internet was given to MIT. And ham radio operators were given 1/256th of the internet. How many did they use? Like 10. You know? And so like, they ran out of IP addresses, like, a long time ago. And so since then, they've been scavenging IP addresses from each other and finding people who aren't using their IP addresses and scavenging them. And they're very, very actively using firewalls and natting. If you guys know what natting is, network address translation. Have you guys ever seen this? You know what a firewall is? So basically, what happens is you've got a Wi-Fi router, right, in your house, I imagine, or a cable modem, or a Uverse box or something. You became acquainted with firewalls in China and at BYU. Yeah, the Great Firewall of China is a little different. It's a different story. So anyway, so what happens is that your local firewall, Wi-Fi router, whatever, has an IP address that's on the internet. It's an IPv4 IP address. All the machines behind it share that IP address. So if you were to go to whatismyip.com, which tells you what your external IP address is, on your PC and on your cell phone and on your laptop that are all connected through the same Wi-Fi router, they're all going to report having the same IP address. And the reason for that is because we ran out. And so everybody shares an IP address. When you're on a cell phone, your cell phone is natted probably with any number of other people. And what happens is that when you make an outgoing connection, when you connect to somebody using one of these connect commands, it connects to them, and then the firewall remembers you connected to Google. So when Google responds, it reroutes it to you instead of to your cell phone. Does that make sense? And if your cell phone connects to Google, then it connects on a different... the firewall basically writes down, okay, this was on this connection. It writes down its connection information. Google responds with that same connection information, and then it will get routed to your cell phone instead of your PC. So your cell phone, your PC, your laptop, they can all connect to Google at the same time, and they're all kept separate by the firewall. The firewall is smart enough to do that. Okay. So, yeah. And so all IP addresses on IPv4 are octets. They're 8 bits, 8 bits, 8 bits, 8 bits. And you basically, when you connect to a server, you type in the IP address, which is this, 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 this. And you might be like, wait, I thought a host name was like wikipedia.org or google.com. That's something called DNS. DNS is domain name service. And DNS translates from google.com to an IP address. So if you... okay. So if you try to connect to google.com, the DNS server, the domain name service server, responds, here is the IP address of Google. You can't connect to that directly. You have to translate it into an IPv4 address, and then you can connect on it. Now, you might be like, well, why didn't they come out with a new version of IPv4 called IPv5? I don't know. IPv5 never happened. I think there was like some prototype or something, and they just moved right on from IPv5 to IPv6. So IPv6 has... This is what an IP address looks like in IPv6. Okay, and if you have a lot of zeros, you can compress those down. So it is, yeah, it's a lot uglier to type, and that's one of the reasons why people don't like it. But it's a much bigger address space. So it uses 128 bits instead of 32, and so that allows enough, for all intents and purposes. Now, IPv6 came out 1995, and it was expected that it would be implemented worldwide within a couple years. It is now 25 years later, and it is still not well implemented. Like, if you... like, Comcast doesn't really support it, kind of. And firewalls, like I was firewalling my Raspberry Pi, and I was having my Raspberry Pi open on IPv6, and the firewall was just like really not like what is this IPv6 thing? And it was because it's just ridiculous that the fact that like major ISPs like AT&T and Comcast don't support IPv6, even though it's been the future for 25 years now, and they're still like we're still slowly rolling out support for it and stuff like that. So what's the difference between a MAC address and an IP address? Did it say MAC on here? So MAC address is your hardware address. So if you have an Ethernet card or your they didn't badly implement it. IPv6 is fine. It's the people who make the routers and things like that, like if you go to the firewall section on my router and you go to IPv6 firewalling, they're like, yeah, we don't really support it, sorry. It's like, why not? We've run out of IP addresses for IPv4 a long time ago, and we're in this like cannibalistic phase of like trying to find anybody who's not using an IP address and stealing their IP addresses. Like, why are you not actively pushing... And Microsoft Windows didn't really support IPv6 until about 7 or 8 years ago. They supported it, but they didn't really. So a MAC address is the hardware address. And so 0014A54. And so it's used by the router to identify a device. So if I turn on my computer, it identifies itself to the router as this number here. And it's like, oh, I know who you are. And it will like oftentimes give me the same IP address I had before. So if I reboot my machine, my IP address doesn't change. And on the router, on the firewall, I can give a name so that this MAC address is associated with my Wii or whatever, and this is my PS5, And so this is a hardware ID. They're not secure. Like, you can change your MAC address by just going into network properties and editing it most cases. Cell phones, they can oftentimes reset their MAC addresses and things like that, but it's oftentimes convenient to leave it the same so that your router is like, okay, that's your cell phone, that's your laptop, and it kind of knows who people are, but it's mostly just used at the router level. Nothing on the internet should see that unless in IPv6 they do something with that. And there's actually a registry of every MAC address made. So there's no duplicate MACs out there. Unless you manually override it, of course. Alright, so coming back to here. How does a server connect to connections outside the local network? Let's show that. So, daytime server. So first of all, how do you host something? You do, well, at the lowest level you do that C nonsense, but here's how you do it using Boost ASIO. So you basically say, I'm going to be hosting a server in IPv4. You can change it to IPv6 if you want, but IPv4 on port 1300. And so every host has different ports that it's listening on. And some of the ports are named, some of them are just free to use for anyone. So I'm listening on port 1300. I just picked that number at random out of a hat. Actually, it's because it was 13 before and I added 2 zeros to it. So FTP is on port 21. And then Secure Shell is on port 22. SSH on port 22. And so there are certain ports that are reserved, and you can't use them on the server unless you have root access. Now, how do you connect to somebody outside of your local network? What you do is you go into your client. Let's take a look at the client side of things here. And you call, actually this thing here, which is what I'm teaching you, you say open a connection to, and you pass in the host name. So www.google.com, and voila, it'll connect to it. How? Okay, so if you put in www.google.com, behind the scenes here, it does a DNS lookup. It goes from the domain name to the octets, the 4 octets. It then makes a connection. It sends a packet to the router, to your firewall. The firewall makes an entry. Okay, this person is trying to connect to Google. So if I get a response from Google using the same token that was passed out, it's going to go back to Bill. Okay, and then it translates it, does network address translation, and then the firewall sends out the packet as if it was the originator of the message, and then that goes through the magic of the internet. All the routers in the world are more or less invisible. If you want to see what they look like, what this looks like, trace route to www.google.com. This is the path that a packet would take. So from the server to Google, that's the IP address of the server. It then connects to Linode. This is a Linode router, probably. Then that is another Linode router, and then that's probably the internal router. That's probably the boundary of the Linode network. It then goes through some nameless routers and ends up connecting to Google here. So it's 10 hops away. So it just went through 10 routers. Well, yeah. It went through 10 routers to get to Google. Trace route www.ucsd.edu. Looks like they're blocking pings past a certain point, but you can trace the path that the network packets take over the internet, and you can see when they block pings. ICMP, the Internet Control Media Protocol, something like that. Control Message Protocol, yeah. And so that's how you can get information on the routing and stuff like that. Why they block them? It's considered a security risk. Like, you're revealing information about yourself. I'm like, yeah, but you're a router. That's your job. I want to know where the routing is going. So, this is interesting. This one responded, and then it blocked the next 2 pings. This one responded, and yeah, and so it could be just quite a lot of packet loss on it, actually. Let's try this again. Let's see if, yeah. So last time 12 didn't respond. This time 12 responded. So it's just dropping a lot of packets. Ping packets have a very low priority, and so they get dropped first if a router is busy. You can do ping-t www.ucsd.edu. Dash T on this one. UCSD is hosted at Amazon now. Interesting. Okay. It didn't used to be. UCSD used to host their own stuff. It looks like they've moved to the cloud. So it looks like UCC's website is now on a EC2 node or something like that at Amazon. So they have a virtual web server now. It's kind of disappointing because it was always kind of a point of pride that we hosted our own things and didn't need to use other people. But that's the trendy thing now. And so with ping, it'll just sit there and ping over and over again, and you can see how long it takes. It's 20 milliseconds to get from the server to UCSD's AWS node. Yeah, and then when Amazon goes down, everything goes down. Canvas goes down. Yeah. And so for my home machine, it looks like it's about 30 to 50 milliseconds. So all this stuff's very interesting, by the way. Like, if you've ever been interested in doing IT stuff for a living, you know, you kind of setting up networks and fixing network connections and things like that. It's always kind of fun, or incredibly frustrating, one or the other. So now we know King Kearney. Thank you. What do you know now? So, the internet. Yeah, that's how the internet works. Cool. Daytime client.cc. So yeah, so basically, if you want to connect to Google, we could probably do that. Let's modify this a little bit. 3 host and port and int. Actually, the port is held as a string, isn't it? C2. So the first parameter is the host, and the second. Why are you mad? Oh, it's argv. Sorry. So the second argument is the port, and so if we compile it, what is NSA's IP address? Traceroute www.nsa.gov. Sorry, that's the DOS. Traceroute. So they're going through an AKAMA system. So AKAMA is a company that does caching. And so what you can do is you can take your website and put a copy of it into Akamai so that people talk to Akamai instead of you. And you can see it's not going any further than that. So basically you offload your... so if people want to DDoS you, they try DDoSing Akamai, which has one of the most powerful networks in the world, and it doesn't work. So... S&P 500, founded 23 years ago, revenue $3 billion a year. And they're basically just a web caching thing. So Akamai has copies of the different websites all around the world, so you can connect to your local Akamai cache. Like maybe there's one here in Fresno. So if I was trying to load the NSA's website here, then that would be... it would connect to the nearest Akamai node and it would return it. So rather than having to go all the way across to the East Coast, it would be at lower latency and faster. And Akamai has this massive amount of bandwidth. And so if your website is just sitting on a cable modem or something, you toss it up on Akamai and then you've got essentially infinite bandwidth for hosting your website. Now, it doesn't help if you have like a database server or something like that you need to actually save data, but for like just websites and things like that, it works really nicely. So, generating foreign intelligence insights, applying cybersecurity expertise, securing the future. Experience the NSA. I want to experience the NSA.
For that, it doesn't sound like much, does it? Hear that? It doesn't sound like much, does it?
That's how hacking works.
But in the hands of an analyst at the National Security
I
Agency,
point at servers too.
signals like these can become one of the most reliable and timely forms of intelligence available.
I like walking to server rooms and just pointing at that's where the hacker is. He's inside of that box right now. I hold my laptop like this and awkwardly type on it while in a data center. Yeah, it's exactly how it works. Okay, good job, NSA. So they're in Akamai. Okay, so let's see. We made this. Okay. Daytime client. Let's connect to www.google.com, port 80. Let's see what this does. Nothing. Let's see. Client, localhost, port 80. Let's see. 1500. Okay, so that works at least. Daytime client. Okay, so what happens here is that's going to connect to a given host and a given port. Every server on the internet has different ports open or closed. It's generally considered bad security practice to allow unrestrained, access to FTP and things like that, because people will sit there and hammer your server trying to guess passwords and things like that, trying to get in. So, in general, you close every port that you don't absolutely need. So if you're running a web server, you have your web service port open, 80 or 8080 or something like that, and you close off everything else. Or you move the port to a different port so that people think that it's FTP, but it's really secure shell or something like that. So what this is doing, that's going to connect to localhost, Google, whatever, on whatever port you specify. And if it failed, then it says unable to connect. What was interesting was that it was just, I guess it succeeded. Maybe. Let's try this. Day, time, client. Yeah, that doesn't work. www.google.com, port 31. Oh, interesting. I wonder if they're allowing that connection. Huh. Connection refused. Yeah. So it looks like Google's allowing connections. They just don't do anything on it. It's interesting. So here's Google. All right. Have you guys ever seen text-based version of Google before? Have you ever browsed the web? Tristan Myers. Oh, you have an IMDb page. That's cool. Where the page doesn't fully load. Yeah, I guess. No, this is just a working web browser that just works on the text system. We salute you, Tristan Myers. ABC 27 in Harrisburg. Interesting. National Toy Hall of Fame. Interesting. Okay. Yeah. What port is that connecting on? Port 80. Yeah, that worked. What about port whatever? No. Yeah, so Google's allowing connections on random ports that don't exist, but it just doesn't say anything. Okay. So Vim, daytime, client. See? And so basically this will connect to the given host on the given port. Port 80 is web by default. If it fails, it prints out unable to connect and quits. Otherwise, we get a line from it, and that's probably what's timing out for whatever reason. And then we just echo it to the screen. And so basically, all the code that you know for like CN and Cout works with networking. So you can just basically CN out of it. Like we could, rather than doing that, we could do like S double right arrow line. And so that'll read one word from the server, and then it will print it to the screen. So that's as easy as I can make networking for you. All the stuff that I was giving you is all background information. The upshot is that you connect to a given host at a given port, and if that succeeds, then you can just use all of your iostream stuff. You can read in it and write in it and things like that. So that's it. That's literally, this is the entire program, you know, and a lot of it's just sort of you know, just error checking, really. So. Okay. Save that. Make. So it just read the first word this time instead of the whole string. And if we look at the server side of things, daytime server.cc. If we look at the server side of things, it sets up, you have to set up a server first so the client can connect to it, right? So you're saying we're to be listening on IPv4, port 1300, and this whole thing just basically sets up, I'm listening on port 1300 now. Cool. And then they use a while true loop that looks a little different. That's a while true loop. And it is going to accept a connection on stream acceptor. There's the acceptor. So yeah, so basically this stream is going to be connected to whatever person is connecting on this endpoint here. So there's a lot of things that get glued together, but basically at the end of the day, you're given another iostream, and you can just see out to it. Use double left arrow. You know. So we have a function up here that returns the time of day. Instead of doing that, we're going to just be like, see out Tristan Myers inducted into the Toy Hall of Fame. And you see, that's going to go over the internet. So once you get all this boilerplate stuff, which you can almost ignore, the only thing that really matters is the port you're listening on. Then you can just read and write to the internet by using double right arrow and double left arrow. So I think this is as easy as I can make it. So let's compile. And I'm going to be teaching a meditation class this Sunday. I don't know if you guys are interested in going to it. Let me know, and I'll give you guys priority on setting the time because I don't have the time set yet. So it's compiled. Daytime server background. Daytime. You know my IP address. Okay, daytime client. Port 1300. So daytime client on 127.0.0.1. Yes, that is my IP address. You should attack it in DDoS that IP address right there. Send all of your weapons at 127.0.0.1. Now you know. Can't make it? Nah, that's fine. It'll be at Woodward Park, Aaron. So just tell me what time is convenient for you, and I'll get something set up. So you notice that in the server, and I'm going to move this because I'm tired of typing this. Server.cc to just server.cc, move daytime client.cc, client.cc, the make file. The server was double left arrowed, Tristan inducted into the Toy Hall of Fame. The client double right arrowed a string, and a string only reads one word. And so if we wanted to client localhost 1500, it just reads one word. And so if we wanted to read more than one word, if we wanted to read a whole line, then we could use get line instead of double right arrow, and then make last client. You don't live in Fresno, so it's going to be drive. It's fine, I guess. And then if we use get line instead, it'll print out Tristan Myers inducted into the Toy Hall of Fame. And you could actually run the client on a different machine. And so you would just connect to www. So for the rather than localhost, which is your localhost, it'd be www.csci4x.com. And you can see on the server right now, it's running a service that every time somebody connects to port 1300, it prints Tristan Myers is inducted into the Toy Hall of Fame and quits. So that's as simple as I can make networking for you. I'll play around with this demo a little bit. I'd like for you guys to just work on your projects this weekend, because we have 5 weeks left in the semester, and a lot of you don't have a lot of work done on your mod or on your project. So I'd like for you to just work on that this weekend, and then I'm going to put together a assignment to do a networked game. I'd like for you to do like Battleship or something like that using networking. Okay. So you should be able to do it just with what I have here. I'm going to kind of package it up and polish it, but basically you could just like see out E7, and then the other thing writes back miss, you know. So let's pull together team for the big win. Yeah. Plus, can we have checkpoints? Yeah. So probably in about 2 weeks, maybe after Thanksgiving. I think that's a good time. I would like to see a proof of concept at least working. Okay. So that'll be a 10-point checkpoint for both the mod and your project, and so that's in like 2 or 3 weeks or something like that. So yeah, because some of us are not the best with time management, and if you don't have like some point-based thing kind of looming over your head, kind of encouraging you to do stuff, then we tend to put it off till finals week, and then everything happens finals week, and our brains explode. So yeah, I'll put in a checkpoint after Thanksgiving. Okay, and I want to see like a working system, so you can backtrack from there to something. And Betancourt is going to be giving a workshop on modding Minecraft. So if you guys are interested in that, you can do that for your mod. So attend Betancourt's mod talk tomorrow, 4 o'clock here. It'll be recorded also if you can't make it, and propose a Minecraft mod. That'll work. Quake mod will work. Skyrim mod will work. I just want to see you guys do something cool. All right. How long do you want the presentation to be? As long as you want. I don't care. So, an hour, 2 hours, 3 hours, an hour, 2 hours, something like that. Somewhere in that range. And it is extra credit for attending the modding talk. So, all right, that's it. 30-minute presentation, 30-minute demo. Yeah, it works for me. So that's it for today, guys. Work on your projects, work on your mods, and I'm gonna get a little skeleton together. I'm pretty excited by this. I think finally networking is gonna be easy enough to work, so and be doable. So we'll do like a networked Battleship game, if that sounds good to you. Battleship's not too bad. Okay. All right, that's it. See you guys.